So today we're going to finish up section 3.1 over functions. This was a really long section in your textbook. So we've taken a few days to get through all of the little topics. So this is part 2 of the notes. In part 1, we learned the basic definition of a function in terms of sets. And here in part 2, we looked at some examples of some common functions in discrete math, like the modulus operator and the floor and ceiling functions. And we looked at a couple examples in a Python notebook as well to see how those were actually programmed here. And this is where I want to start my review really for today. So this is what we learned last time. We learned about one-to-one functions and onto functions. And these definitions are important. We'll need to know them to finish up the section. A function is one-to-one if for all points x1, x2 in your domain, the things that you're plugging into the function, if the function value at those 2 points is the same, then the 2 points had to originally be the same. And flipping this around using the contrapositive, this is another way of thinking about it. If you start with 2 different points, then you need to get 2 different values out of your function. And this is the way that I actually prefer to think about one-to-one functions. Here, the second way. But this way is usually the way that you see it defined in a textbook, like ours. And the way this works out on these nice little arrow charts, arrow diagrams that we drew, is that a function is one-to-one if the elements in your codomain have at most one arrow pointing to them. So this one is one-to-one, whereas this one is not, since there are 2 arrows pointing to the element A. Okay, so that was one-to-one. And then we also discussed onto functions. So this is a little bit different than one-to-one. Well, of course, it's different. It's a different definition. But this one says that a function is onto if for every element in the codomain, your target set, let's say, then there's an element that you can plug into your function to get to that target. Okay. So for every element in y, there exists an x such that f of x is equal to y. And in the arrow diagrams, what this works out to is each element in the codomain, your output set, needs to have an arrow pointing to it if the function is going to be onto. So this one is onto, whereas this one is not, because there's not an arrow pointing to the element C here. And this is where we're going to start the new material today on page 6. We're going to look at functions that are both one-to-one and onto, because these play an important role in math, whether it's discrete math or any other math subject. And these functions that are both one-to-one and onto are what are called bijections. Something that we didn't talk about too much in, or something that I really didn't mention in the lecture. There are other words for one-to-one and onto. One-to-one is sometimes referred to as the injective property, whereas onto is sometimes called surjective. So the bijection means it's both by for 2, it's both injective and surjective, or both one-to-one and onto. So if you see these words in your textbook, you should know that they refer to one-to-one for injective and onto for surjective. So the reason why bijections are so important, functions that are both one-to-one and onto, is this. If f is a one-to-one onto function from the set x to the set y, then we can define this new function called f inverse. And the way that you get an f inverse is by just reversing the order of your ordered pairs of your original function. So the ordered pairs of f inverse are y comma x, where x comma y was one of your original ordered pairs in the function f. And I already said this word. So we use this symbol f with a little -1 written like an exponent, and this is called the inverse of the function f. So we're not going to go into detail about why one-to-one and onto functions, bijective functions, have inverses, but I believe if you wanted to know, you could check that out in your textbook. There's a little bit of proving that we would really need to do if we wanted to sort through the reason here. Okay, but for us, since we're just mostly interested in using functions and using them to solve problems or program, we don't really have to worry about those details too much. What we want to do is maybe get some practice with this definition for inverse functions. So let's look at this example. Oh, and maybe before I do the example, I'll add a little note here to relate the ordered pairs back to the more normal functional notation. So remember, this is the normal way to write a function. You plug an element n and you get an output. So f of x equals y would correspond to the ordered pair x comma y in the function. So if this is your normal input and output, then f inverse reverses this. So f inverse of y is equal to the original input, x. Okay. So first, let's look at these ordered pairs and compute the inverse. And remember, all we have to do is reverse the order of the ordered pairs. There's not a lot of thinking that we have to do here. So 1 comma b becomes b comma 1. 2 comma c becomes c comma 2. And 3 comma a becomes a comma 3. Does everyone follow along so far? Okay, so this is the mechanical way to find the inverse. Let's go ahead and make an arrow chart for both the original function f and for f inverse. So for f, I would have 1, 2, and 3 in my first column, and then a, b, c in my second column. And remember, we draw an arrow from the first element to the second one. So an arrow from 1 to b, and then an arrow from 2 to c, and then an arrow from 3 to a. Maybe we'll add some labels here. Here's my domain X, here's my codomain Y, and maybe I should specify up here, since we haven't really written out a few of these things. So X is the set 1, 2, 3. Y would be the set containing A, B, and C. And then what I can do, instead of making a totally separate chart for F inverse, what I'm going to do is just add a third column with the elements of X again. Because remember, F inverse is just reversing the order of things. And then I can draw my new arrows from B to 1. From C to 2. And then from A to 3. And if you follow the arrows from left to right, you can see that F inverse here, the second function, undoes what the original function F did. So 1 is mapped to B, and then B is mapped back to 1. 2 is mapped to C, C is mapped back to 2. And then finally 3 is mapped to A, and A gets mapped back to 3. So F inverse sort of untangles what F did originally. And the arrow directions are actually just reversed, if you want to think about it that way. Maybe I'll make a note over here about the domain and codomain. So if X is the domain of F, and Y is the codomain, then Y is the domain. We're reversing the domain and codomain. So Y is the domain of F inverse. And X is the codomain. So just something to keep in mind, this reversing. Any questions about the example? Okay, so those are inverses. Now we'll talk about compositions of functions. So this is a way to put two functions together. And for this, I need two functions. So let g be a function from x to y, and let f be a function from y to z. Then the composition of f and g is a new function And we use this notation in math for composition. We put a little circle, a little open circle in between the two functions. And the way this works is that you're plugging G into F. So you're kind of stringing them together. Excuse me. Let's try that again. F of G, and then if I try to plug an element into it, what I do is I first plug the element into G, and then I plug the result into F. So in function notation, it would look something like this. So X is first plugged into G, and then that result is plugged into F, if you want to untangle the parentheses. So maybe I'll make a little note down below here that when you're thinking of composing functions, you're thinking of plugging one function into another. This isn't precise language like this is. This is just a convenient way to think about it. We plug G into F when we compose them. Okay, it looks like my internet connection. Actually, I think it was just my connection to the Zoom server cut out there. So hopefully you heard everything I said before it cut out. So what I was saying just before I lost my connection is that when we compose two functions f and g, what we're really thinking about doing is plugging the function g into the function f. And this is something that you've probably seen in your other math classes. Just want to make sure that we go through in detail how this works so that we have a really good concrete understanding. Because composing functions together is just like taking the output of one program and plugging it into another program. It's really an important idea in computer science. Okay, so first of all, I want to think about how composition works with our ordered pair definition for functions. And then our next example, we're going to look at the more normal functional notation. For this particular example, my sets x, y, and z are going to be as you see there. So x is the set with 1, 2, and 3 in it. Y is the set with a, b, and c. And then the set z is the set with x, y, and z. And then I have two functions that we're going to compose together, these little sets of 3 ordered pairs. F is this set, g is this second set. And this tells us where functions get mapped. Okay. So what I want to do, like I said, is compute the composition f of g. So this is a new function. And we'll use the set notation to be consistent. Sets of ordered pairs. Okay. So before we get to the writing the set, let's set up a arrow diagram for both f and g. So you can see the order that things have to go. Things are mapped from x to y by this function, g, and then f maps elements from y over to z. So in my arrow chart, I'm going to start with the set x, the numbers 1, 2, and 3. And then these are mapped by g to elements of y. And they're the letters A, B, and C. And then finally, f is going to map to z, which has the letters x, y, and z, lowercase z in this case. So g, we can work through the arrows. One gets mapped to A, 2 gets mapped to A as well, and then 3 gets mapped over to C. And then we can fill in the arrows for, oops, this should be a G. We can now fill in the arrows for F from A to Y. From B to X. And then from C to Z. And then in order to figure out the composition, we'll follow the arrows from the left, X, all the way over to the set Z. So for example, if I want to figure out where 1 is mapped by the composition, I would follow the arrow from 1 over to A, and then the next arrow down to Y. So maybe I'll start writing my set now for the composition. 1 gets mapped to Y. Where does 2 get mapped to? Someone want to tell me the answer? Where does 2 go? Right, so 2 gets mapped over to Y as well. And then we have one more element. Where does the composition map 3? Z, good, yeah, just follow the arrows directly to the right. Good. So this is the composition. Does anyone have any questions over this first example? Okay, so since it doesn't seem like you guys have any questions about that one, let's go ahead and move on to this last example. And what I want to do is actually break apart this given function f from the real numbers to the real numbers, where f of x equals the square root of 1 plus x squared. I want to break this apart into the composition of functions, of several different functions. And in order to do that, what I want to think about is what happens to what we're plugging in. So when we plug in x, maybe I'll just start writing here. We plug in x, the first thing we're going to do is square it. So we square x, and then whatever the result is, we're going to add 1. So add 1 to the result, and then we're going to take that value and take the square root of it. So maybe I'll say take the square root of the second result. Okay. So let's think about each of these steps as a separate function. So this first step, squaring, that would correspond to just the square function. Maybe we'll call it g of x equals x squared. And then adding 1 to the result, that would correspond to another function, just taking a value and adding 1 to it. And then finally, we take the square root of something. That would be maybe a third function. I'll call it k. Just a single square root. And when we string them all together, we square something, we add 1, and then take the square root. We get the overall function f. So that's how we break it down into pieces, and now we just have to string them back together. So f of x would be equal to first squaring, then adding, then taking the square root. And we have to go sort of in the reverse order of that when we're thinking of compositions. So the first thing to do is to square, that's g. Then we take this result and we plug it into h to add 1. And then we take that result and plug it into my last function, k. So using the composition notation, this would be k of h of g. Good. So that's the answer. That's what I was looking for. Does anyone have any questions over this last example? Okay, so that's our stopping point for today. But I do want to point out that this process of rewriting a function as a composition is actually an important skill, I think, in computer science, because oftentimes when you're trying to solve a problem or write a program, you have an idea of what you want your result to be. You know what you want to get out of your function. But in order to program a computer to actually do that, you'll have to break it down into a step-by-step process that you can write a program to do. So this breaking down a function into pieces is actually a skill that you guys might need.